Hello again. It's been a while since the last video, which wasn't a most enormous success, partly because I was still working on a breadboard. So as you can see, we now have the a prototype of the synthesizer, just put together on a bit of matrix board here. This control panel is sort of cobbled together from, this was the start of a previous version of a control panel for something, and this was something else, and they fit together. So there we go. And you've got a volume control, audio out, MIDI in, USB power, and these are the controls, two switches and the LED, which tells you which control bank you're in. Now you may notice a sort of ticking noise on the audio. Unfortunately, this is due to some crosstalk from the MIDI, which wouldn't be in a final version. So, well, it's annoying me like hell, but try and get past it. On the board, you can see this is the microcontroller. That's the one chip in the title, and then I'm not counting those as chips because they're just op amps. In this case, they're Texas Instruments TLV2374s, but I'll probably switch to Microchip 604s because they're cheaper. The crosstalk may partly be due to the fact that, for simplicity and the ability to swap things around, I've got this ribbon cable which is carrying both audio and controls, and it's actually an old hard drive cable from the days when we had ribbon cables for hard drives, and I've got a bunch kicking around that have been sitting there for years doing nothing. So, you know, it's quite convenient. Probably wouldn't stick with that, but it has made me think of having some sort of bus system for these things, but that means sorting out pin outs for all the modules and everything, but it makes it easy to plug the controls in and out of the board. So anyway, how does it sound now? So if you managed to power your way through the last disaster of a video where everything kept breaking, you hopefully notice that that sounds rather richer and fuller than it used to, than the previous version did. And that's because the previous version was just a single oscillator, which was really my original design goal. My first ever synth had one oscillator, and I thought that's adequate-ish. But it was a bit weak. This is the same sound with that one oscillator. Which you could beef up with some effects, but you probably don't want to have to do that. So what we have, well, the normal approach is to have three oscillators, and we sort of have three oscillators. I've called it an ensemble oscillator because it contains three identical blocks, but only one control voltage. So it's sort of one and a half, well, no, it's three oscillators, but they're not completely independent. So when we switch, you get this. Which, as you can hear, is a much richer sound. And I'm going to go over the design of that with you now. Let's just hear it in the higher registers. And I'm just going to switch to a sawtooth wave here. So as you can hear, hopefully, even if you're not using pulse wave, so you haven't got any pulse width modulation, you can still get quite a thick sound. It's also running through the filter, but I'm not going to talk about the filter today at all, much as I love talking about the filter. So let's just look at how oscillators work. There's a couple of main approaches to oscillators. I'm just juggling stuff on my desk here. I'll trap my mouse. Oh well. The first one, which was in my Moog Prodigy, what I had all those years ago, uses a pretty straightforward principle. If you imagine starting off with a capacitor like this, connected to ground, or it can be connected to any voltage really. And then we put in, I can never remember the symbol for this, but we put in a current source. Now this is a constant current, okay? So it might be, it's going to be very small, but it might be sort of 0.1 milliamps or something. That current charges up the capacitor, so the voltage will get higher. If we measure it here, the voltage will keep going up until it reaches the limits of the power supply, and then it would just do that. Now, because it's a constant current source, it's going to be a straight line rather than doing what capacitors like to do, which is to charge up really rapidly and then slow down. So it's not an oscillator yet. We've got the voltage out there. This is ground, by the way. So what you want to do is to somehow discharge the capacitor again, and you can put a switch there of any kind. So it's usually a transistor, might be a JFET, and then you connect that switch to some sort of voltage detector, which might be a comparator, say. Oh whoops, I'd have to go around there. So the comparator tests it against some voltage here, and when it gets to a certain point, let's say it gets to there, the comparator switches on, shorts out the capacitor drops down really rapidly again to 0. The comparator switches off and it goes through the cycle again. Now from that you can get all your basic waveforms. You start off with the sawtooth. There's a couple of ways to get a triangle wave out of that. The Moog Prodigy, at least, has a transistor which starts conducting halfway through the voltage, and so it chops it off like that, which is one of the reasons it's, I mean, the triangle wave is a weak and feeble wave at the best of times, but it's very feeble on the Prodigy. If, on the other hand, you put that through a comparator which switches on and off, a different comparator to that one, which switches on and off at some level here, then what happens is that you get a pulse wave out of it and a square wave out of it. Now that's a pretty good type of oscillator, but it's not very good for digital control, which of course the MCU is doing, the microcontroller is doing here, because the only way to control the frequency of it is to control the point when it's reached such a voltage that that comparator kicks in. And in order to do that, you've got to very precisely control the current here. Now that's fine on an analog circuit. That's coming off the control voltage anyway, and you've got a voltage to current converter. And so, but this oscillator is tied to the fact that it needs to complete its cycle in order to repeat. And probably most people just call that a sawtooth oscillator, or a sawtooth based oscillator. Now there's another way to do it, and that is to start with the square wave. So I'm not sure if I'm drawing the right thing here, but let's see. The square wave comes in. Now let's suppose we have some sort of circuit that can detect the start of the square wave or the pulse wave, and then as soon as it's gone up, start discharging or charging something. so that it will form a sawtooth wave. And that's what a wave shaper does. It's actually electronically, it's an integrator, and the simplest way to do that is to take an op amp like this. You all know what op amps are, I'm sure. You put a capacitor across it like this. Sorry. And then you can measure, then you take the voltage out here, and you put your current, however it's drawn, in here. And then you just have that might be tied to ground or an intermediate voltage. Now I'm going to be using an intermediate voltage, we'll see why in a minute. So what happens is that if you just throw in a square wave there, you actually get a triangle wave out. Let's draw our triangle wave here. Because the same amount of current is going in on the up and the down, it will slowly charge up and then slowly discharge like that, and then slowly charge up again and slowly discharge like that. Now this approach is used by, in fact, the Juno 6 and 106 oscillators do this. So you've got the same thing. How do you get a sawtooth wave from this? And the answer is back to another switch. What they do is they put a switch, again it's a transistor, across here, and they actually, sorry, let's go off in that direction, they actually send a pulse to that at the start of the wave. So they're sending two signals to the oscillator from the Juno. I'd show the circuit diagram, but it's very complicated. The square wave's coming in, and they're also sending a little pulse at the start, which shorts that out so that that can start charging up again. Now it's actually worth just looking, whoops, oh dear, I've ruined all my paper. It's actually worth just looking at why that works, because it is educational. If we have an operational amplifier, let's imagine for a moment we've got two voltage rails, so we can connect that to the middle, we can connect that to ground. So the op amp is powered by +5 and -5, or +10 and -10. As you're aware, this synth is designed to all run off +5, but which is why I've generated a 2.5 volt rail. But anyway, op amps have a characteristic. They try to keep the negative input at the same voltage as the positive input whenever possible. They'll do anything they can, and that's the magic. So this tends to be called a virtual ground, because let's suppose we connect two resistors like this, and we have some voltage here. Let's say they're the same voltage, the same resistance, I mean. The op amp will attempt to keep that at 0 volts, which the plus is at. Now how can it do that? It can only do it by adjusting its output voltage. It can't adjust the input, it can only adjust the output. It's trying to set the input and it wants to adjust the output. So let's say that's at +2 volts here. Now you've now got the equivalent of a voltage divider across these two resistors. So if that's got to be 0, now you see the resistors are both the same resistance. So that should be on the midway point. The only thing the poor op amp can do to keep its input at the right voltage is to switch the output to -2. And now the middle of those two resistors is at 0, and it's happy. And this is basically how all op amp feedback loops work, negative feedback loops work. If you double that, if you switch that to 2K, that's no longer in the middle resistance wise, because the equivalent voltage divider or potential divider would be this. It would be 1K and 2K. That wants to be at 0. That wants to be at 2 volts. So the op-amp this is connected to the output. So the op-amp needs to shift that to a voltage which will pull that down to 0. So it needs to drop twice as many volts across there, because there's 2 volts dropping across there. So it needs to drop 4 volts across there. So the only solution is to take that down to -4. Or have I done that the wrong way around? No, I haven't. So that it can drop the correct amount of volts across there. And that's why the ratio of these two resistors in an op-amp will set the output voltage, the gain across the op-amp, because now that's double what that is. If, on the other hand, you halved that, it would now only have to drop 1 volt across there, so the output would only go to -1. And the smell of this pen keeps making me cough, which is a bit worrying. I do apologise. So, why am I telling you this? I've forgotten. So yes, so if we put a capacitor there instead, in our oscillator, the current is coming in here, or it might be going out here, doesn't make any odds, but let's say it's coming in. The current is flowing in, and it's flowing into that capacitor. That means that the voltage on the capacitor is starting to rise like that. So that means it's dropping so many volts across there. Let's say it's charged up to 1 volt, right? Well, we know that has to stay at 0 volts there, and there's 1 volt across the capacitor now. So all that the op-amp can do is pull its output down to -1 volt, and then it's 0 there, and all is right in the world. And it's important to remember at this point we're talking about a current, not a voltage. We don't care what the voltage is here. It doesn't matter. It's a current coming in. Current modes are somewhat different to voltage, to thinking about voltage, but currents are more fundamental in a sense. What this does is, because this is, let's say there is some voltage here. We don't care what it is. But I suppose I'd better think of one. So let's say it's 2 volts here. And this is 1K, 1000 ohms. Well, we all know Ohm's law, don't we, children? Which is that V equals IR, where I is the current, R is the resistance, and V is the voltage. So that means I equals V over R, which is 2 over 1000, which is 1/500th of an amp, which is 2 milliamps. So we have 2 milliamps current going in here. So we don't, the voltage could be, if you had 4 volts and a 2k ohm resistor, it would be exactly the same amount of current going in. So that amount of current flowing in will gradually charge up the capacitor, because that's how a capacitor works. You have 2 plates, electrons flow in, and a voltage develops between the 2 plates. So that forces this voltage down. That means there's an increasing voltage across the capacitor, and that means that the current flowing in will stay constant and the charge will stay constant. So instead of it going up like that or like that, the voltage on the capacitor, it goes up in a nice straight line. So you've got your potential sawtooth wave. So all you've got to do is change the voltage here, and you get more current going in, and the it will charge faster or slower if you reduce the voltage. And in fact, even more cool, if you take the voltage negative of the plus input here, the positive input, it'll start discharging the capacitor again. So you can do a push-pull where you can get a triangle wave. We've still got to discharge the capacitor though, rapidly for our sawtooth wave. How are we going to do that? Well, one simple answer is this. Let's suppose it's you've got a fair, let's say we've got our 1 milliamp, or it's going to be smaller than that for an audio oscillator, coming in like this. If we just throw that voltage very rapidly south, if we suddenly suck a load of current out of the voltage, what am I talking about? Let's try again. If we suck a large amount of current back out in this direction, we're going to discharge the capacitor again without the need for a switch. We don't need that switch across there. We can just pull the current back out. I hope this is making sense. So current going in slowly, there's a little current there, and then if we pull a large current down, we can discharge the capacitor again, and then we switch that current off and up it goes again. So that brings me, I think it's time to show you the oscillator block circuit diagram. If I can just get my mouse working again, and dear me, transition this scene. No, not going to work. Oh right, got to do that. This is the actual ensemble oscillator block. As you can see, oh, you can't see my fingers now. There are 3 op amps, all configured as wave shapers like that. Now, what comes in here is the control voltage. That's setting how fast the ramp is, and it comes in 2 bits, a high value and a less significant value, because it's actually coming off 2 digital analog converters on the microcontroller, because there isn't sufficient resolution on a single one. That comes in here at 2 different resistors. Now those 2 resistors have a ratio of almost exactly 32 to 1. Which means that the top value is the 5 most significant bits of the digital to analog conversion, and then the rest are on the low value. 1 meg 5, that's 1.5 meg ohms and 47 k ohms, and when you add them together, that's the amount of current flowing in to the capacitor to charge it. And this is where a little bit of magic occurs. There's a square wave which may or may not be coming in here. These 2 inputs are switched on and off by the microcontroller to set what waveform we're going to get. If they're both on, and they're both connected to the same pulse wave output from the microcontroller. So if that one's switched on, every time the wave goes positive, that diode will conduct. You'll then get a huge surge of current relatively through this small 1K resistor, which is much smaller than these resistors here. Likewise, when the down square wave is working, then when the waveform goes down, it sucks back out again, so that'll give you a square wave. If you switch one of them off, you'll get a sawtooth wave, because let's say the up one is off and the down one is on. Every time that goes down, it will clamp the voltage back down to the lowest possible value, and then it will trickle current back in via these ones from the DACs, which will slowly charge it up again for your ramp wave, if that makes any sense. And these three resistors, they're just mixing the outputs onto a single bus. Now this is why they aren't three truly independent oscillators, because the ramp has to have the same value for each oscillator. But that's not too bad, and I'll show you why. We're not trying to create a perfect signal generator here. We're not interested in what it looks like on an oscilloscope. We're interested in what it sounds like. So if the ramp length is a bit off, it doesn't matter. So for instance, let's suppose our we have our wave here. That's wrong. Right, for the sawtooth wave, what it does is it sends out a very small pulse like that, which pulls the sawtooth vertical, and then it's also got a slow control voltage which will drive it back down again. So it's up there, and as soon as that switches off, it starts going down again. Now the thing is, if it's a bit off, if it's like that, it doesn't matter. If you actually listen to the difference between this and a perfectly accurate sawtooth, it's negligible and even a bit more interesting. This flat bit here doesn't matter. So you can vary the wave quite a lot, and it sounds fine. It might even sound a bit better, a bit more interesting, because it's a little bit of a shark tooth wave rather than a sawtooth. Now, however, we've still got the what do you do about a triangle wave? Because if you've got a constant control voltage, it can only pull in one direction. It can only pull down, or it can only pull up. It can't do both. So what this does is to, when we ask for a triangle wave, I'll just do one. Don't know what it's going to sound like on this. That's the boring old triangle wave. Then it actually is switching the control voltage. Both of the pulse inputs are switched off, and it just switches the control voltage, which is through the high resistance inputs, up and down, and that produces a boring triangle wave like that. I'll just switch back to that. So when the triangle wave is running, these inputs, all of these, are completely off, and it's just got low current flowing in from these common high impedance inputs, the result of which is there is only one triangle wave coming out. It actually switches one of the oscillators off altogether, and the other two are just locked together on that, on those inputs coming from the control voltage here. Nonetheless, I don't think many people want full sounding triangle waves. The whole point of it is it sounds a bit like a sine wave, and you just want it a boring sound for making, you know, eerie noises in a 1950s style. But the result of this is you can get some very nice sounds. Let me just switch back to that. Very confusing when you've got two displays showing the same thing. So that is actually at maximum spread. And what it's doing there is it's taking the pitch and it's shifting one of the semi-oscillators up, and it's shifting the other one down by the same amount, so it all stays in tune, but you get this more convoluted sound. And there it is in mono. And you can throw in some, this does do pulse width modulation, so you can throw some in as well. Which produces some nice phasey sounds. So that's about it really. After the basic oscillator block, as I've christened it, the it goes in from the OSC bus here. It then goes into the filter and then into the VCA, and it's treated normally. So that was the basic oscillator block. If you've got any comments or anything you want clarifying, because I think I waffled a bit there, if you've got anything you'd like to clarify, please comment. And of course, if you've stuck it so far, please like and subscribe, and it would be lovely to get some attention on the channel for this synthesizer design. The one thing I do want to say is that there's been a certain amount of what am I trying to do here? Am I trying to make the world's smallest or most simple synth? Or am I trying to make it, you know, as comprehensive as possible? And there's always a balance between the two, because going for the most options, you're going to end up building a Moog modular or something. Whereas if you go too simple, you end up with something boring that's not very much use. But I think this is sounding quite versatile now, and as you can see, it's a very small design for a mono synth. This is, you know, £2 something for that, and the microchip op amps are less than £1 each, and then these other components are very, you know, negligible amounts of money. So it would be a feasible sort of design for some sort of poly synth, which is one of the other reasons I'm looking at defining some kind of bus here, rather than just having it as a mono design. But that's all. I've been going for over half an hour, and YouTube doesn't like that apparently, I don't think. So anyway, that's the end of the video.